All right, see Lindelof videos. Optimization problem number 2. Turns out that you are building a cylindrical barrel, and it must have a volume of exactly 1 cubic meter. The material for the lateral surface costs $18 per square meter, and the material for the circular ends is $9 per square meter. And the question here is, what are the exact radius and height of the barrel so that cost is minimized? First thing I'm going to do is this. I'm saying, you know what? First thing you're looking for in an optimization problem is what's to be optimized. So you're looking for what's to be maximized or minimized. Once you figure that out, you've got this thing under control. Also, they give us some pretty specific information. One, we know we're making this barrel. So my first question is, because I'm dumb, maybe, possibly, probably, is does my barrel have ends on it? And if my barrel does have ends on it, how many ends does it have on it? And it tells us that it says circular ends, plural. Therefore, I must assume that we're going to be putting dead bodies in this barrel, right? Or $11 million, right? So we have that end, and we have this end here. And I'm just trying to get an idea of what we have to pay for, right? We're manufacturers, I guess. And then also we have this, don't we? We have this lateral area, this area around the circle. I'm sorry, around our cylinder. So this cylinder is going to be contained. First thing I'm going to do is write down some stuff that I know. For example, happen to know that volume of a cylinder is equal to pi r squared h. Also know, right, because we have to have this volume here. We know that the volume is going to equal 1, so that's going to be helpful. We also know that this thing is going to have 2 ends on it, so we want the area of a circle, and the area of a circle is pi r squared, isn't it? So we have the area of our circle there, and we also know that we have this lateral surface area, and our professor would have given us this equation for lateral surface area, which happens to be 2 pi r h, so 2 pi r h. I always get the question, will you be given the formulas? Hell, I don't know. Let me say this, though. If you are given the formulas, you should at least have a general familiarness with them, because you don't want to be learning it as you're going. I mean, it might be good to help you memorize it, or to help you, to reassure you that you're on the right track. But I wouldn't go in there saying, I'll worry about what those formulas are when I get there, because that's going to make a mess, I think. That's my opinion. All right, so we also know that we're going to minimize. Here's another fact that we know about optimization problems, is that we need 2 equations. We need 2 equations. One is the primary and one is the constraint. I think our constraint, because it says here the volume is 1 cubic meter, I think our constraint equation, sometimes called secondary equation, is that the volume, this is, I'm here right now, I'm taking this and I'm saying, you know what, the volume is 1 is equal to pi r squared h, because it says that our volume must be 1, so volume is 1. So I made the volume 1, and I'm going to call this secondary. If you're at Harvard right now, you want to call it constraint, but for now, secondary if you'd like. Then I'm going to start writing the primary equation, and the primary equation has to do with the cost. So the cost of this barrel that we're building is associated with two things. It's associated with the cost of the lateral area and of the 2 ends. So 2 pieces. So the lateral area, it says here, cost $18 per square meter, and that lateral surface area is 2 pi r h, plus we have to put the ends, and those, it says that the material for the ends is $9 per square meter, so $9. Remember, we have 2 of those, so that's what this 2 is for, 2 area of circle, so 2 pi r squared. I am going to go ahead and simplify this a lot. And when I simplify it, it's going to come out looking like this, that the cost is equal to 18 times 2 is 36, so 36 pi r h, plus 9 times 2 is 18 pi r squared. Here's the rub now, and this is a serious issue, is that we have this equation in forms of 2 variables. We have the variable r for radius and the variable h for height. So what I'm going to do is I'm going to solve the secondary equation in terms of this. So this h right here is this h right here. So if I solve this, if I just divide both sides by pi r squared, I get this 1 over pi r squared is equal to h. Now hopefully you can see I have h is this thing, and it's in terms of r. So I'm going to go back, I'm going to do my substitution, and I'm going to say, you know what I think I'm going to do, if you don't mind? I'm going to hold on to this for a second, and I'm going to put this in while I have it, right? So I take out this h, but I'm going to put h back in, and I'm going to put h in the form of r. So pi r squared, plus remember that we had this other piece here. So plus this 18 pi r squared, right? So far, so good, I think. Here I'm going to simplify a little bit, and I'm going to go ahead and do some algebra as I go and try to clean this mess up as I go. This is what I'm seeing. I'm seeing this r right here and this one down here. I'm seeing pi here and pi here. So this is one factor of r. This has two factors of r. So this thing turns into 36 over r, doesn't it? Yeah, 36 over r plus 18 pi r squared is equal to our primary function. And I should have named this right away. That was a mistake, seriously. This is the primary equation. So primary equation, your professors really care about this crap. So there's that. Now I'm going to start to take the derivative. And one thing I'm going to do to make it easier for me to take the derivatives, I'm going to rewrite this as 36r to the negative 1. I'm just bringing it up out of the denominator and bringing it up so I can differentiate more easily. So I'm going to differentiate here. If you claim that you're going to take dc dr, the derivative of cost with respect to radius, that is true. But if you accidentally call it the wrong thing, you're wrong. So what I say to most students is just call it the first derivative. Do you know what I mean? Because that is right. I am taking the first derivative. And the first derivative here is 36 r, I'm sorry, it's negative 36 r to the negative second power, right? Plus 36 pi r. Be careful here. I see people screw this up all the time. I want you to say this to yourself out loud. I'm not even joking. Pi is a number. Pi is a number. It is not a variable. So don't let that get into your mind. It will really screw you up. So please. Now I'm going to look for my critical values. I'm going to look for my critical values here, or my critical numbers. So critical numbers here. So I'm going to set this thing equal to 0, negative 36. If you don't mind, I'll put r over 2 plus 36 pi r. If you want me to, let me know, and I'll go back and show you how I solved this, but I'm not going to right now. So what I am going to tell you is that I solved this out. I did my algebra, my arithmetic here, my algebra, and I got that the radius was equal to 1 over the third root of pi. And check this out for a second. This is really important. To find my h value, h is equal to 1 over pi r squared. So h is equal to 1 over pi r squared. So what I'm going to do here is this. I'm not going to do the work because I'm going to save you the time. But here is that value. So I would put that value inside here, and I would solve and get that value back. So, and I think it's the same value. Thank you so much for watching. I hope this is helpful. This is really important math. I have people ask me, when the hell will I ever use calculus? This is math you would use. This is something that a scientist would use. Something certainly that a very, very successful business person would want to know. An economist, etc. So thanks for watching. If you have any questions or comments, let me know. And if you haven't already subscribed, please do. Thanks.